We are in the chapter of the real numbers, and in the last class we have done exercise 1.1 where we have seen we have solved the problems which are based on rational numbers. Today we will see the irrational number. At the very outset I have told you that real numbers can be classified into two categories: rational number and irrational number. Those numbers which can be represented in the form of p by q, where both p and q are integers, q not equal to 0 is a rational number. And those numbers which cannot be represented in the form of p by q, where both p and q are integers and q not equal to 0 is called irrational number, simply. Now the second difference between rational and irrational number is that the decimal representation of rational numbers will either be terminating or non-terminating repeating, and the decimal representation of the irrational number is always non-terminating, non-repeating. We will learn it in details later on. The third one, both the numbers, it is not exactly the difference. Both rational number and irrational number are the parts of real number, and any real number, whether it is rational or irrational, that can be plotted on the number line, which is known as the real line. Today we will start with 1.2. So once again, let me classify the things like this. Real number, see the classification. Rational number, irrational number, rational number, natural number, whole number, integers, and fractions. Integers, positive integer, 0, and negative integers. So now in this exercise we are going to discuss the irrational number. First, suppose you are supposed to give some examples of the irrational number. You will write the numbers like this: 5.03, 003, 0003, 00003, ... See the number very carefully. Number is such that it is neither terminating nor repeating. You cannot put any recurring marks over any digit after the decimal symbol. So it is an example of irrational number. Suppose you are writing 5.26, terminating, and if it is terminating, then it is rational number. This one is non-terminating, non-repeating, therefore it is irrational number. Now again I am writing one number, 1.253, recurring over 53. It means 7.253535353 ... Its expansion will be 7.2535353 ... This is also non-terminating but repeating. So rational numbers are always either these rational numbers either terminating or non-terminating repeating. repeating, either terminating or non-terminating repeating. Whereas irrational numbers are always non-terminating and non-repeating. Examples 1.5, example of rational number. 2 by 7, rational number. 1.35, 2 recurring over 2, rational numbers. Example of irrational number. 1.21, 221, 2221, ... or put any, within the square root, put any number which is not a perfect square or perfect cube. Suppose we are writing here 3. You cannot take this 3 out of this radical sign completely, and hence it is irrational. See, cube root of 5, again irrational, because 5 cannot be taken out from this radical sign completely. But if we write square root of 4, 4 can be taken out of the square root sign and it will be 2, which is a rational number. Remember, similarly, root 16, cube root of 27, all these are the examples of the rational number. So, this is the basic difference between the rational number and irrational number, but both this rational number as well as irrational number can be plotted on the number line. With this much of information, we can start with the exercise of 1.2. The first question states whether the following statements are true or false. Justify your answers. First question is, every irrational number is a real number. See, every irrational number is a real number. Here is a rational number. It is a type of real number. So, every irrational number is a real number. Yes, this statement is true. The reason is irrational number is a part of real number. The another part is rational number. Every point on a number line, yes, see this question, second of question number 1. Every point on the number line in the form of root m. Every point on the number line is of the form of root m, where m is a natural number. Okay. Natural numbers means 1, 2, 3, 4, ... And put the value of m equals to 1, it is 1. Put the value of m equals to 2, it is root 2, root 3. So, root 4, that is 2. So, what we are finding? If the m assumes to be a natural number, then root of m will either be rational or be irrational. It can be rational, it can be irrational. The question says that every point on the number line is of the form of root m, where m is a natural number. Whether true or false? Yes, it is a true statement. Because whatever may be the value of m, if m is a natural number, it will either be a rational number or it will be an irrational number. Now, in both the cases, we know that it is a real number, and real number can easily be plotted on the number line or the real line. Every point on the number line is of the form of root m, where m is a natural number. True. The statement is true. Very true. The third one, every real number is irrational number. Every real number, see this classification. every real number is irrational number. See, real number can be rational or irrational. So if we are saying that every real number is a rational number, that is not true. That real number can be irrational number or it can be a rational number. Hence, the third statement of the first question is false. Now come to question number 2. Are the square roots of all the positive integers rational? See, the second question of this exercise 1.2. Let me discuss it. Hope students you are following what I mean to say. Question number 2 it is, are the square root of all positive integers are irrational? Remember, positive integers. What are the positive integers? Positive integers simply means natural numbers that starts from 1, 2, 3, 4, likewise up to infinity. Now the thing is, are the square root of all the positive integers irrational? Now take an example. Square root of 1, rational. Square root of 2, root 2, irrational. Why irrational? Because 2 cannot be taken out of the radical sign completely. Square root of 3, that is root 3, again irrational. Why irrational? Because the reason is because 2 and 3 are not perfect square numbers. So, if the radicand is not a perfect square, then it will become an irrational number, and if the radicand is 4, which is a perfect square, that becomes 2, which is a rational number. Now, the question says, are the square roots of all positive integers irrationals? No. If not, give an example of the square root of the number that is rational number. Yes, square root of 1 is rational and 1 is a positive integer. Square root of 4 is 2, which is the rational number. Similarly, take any number which is a perfect square root of 9, square root of 16, square root of 25, square root of 144. All these are the examples of rational numbers. But if the radicand is not a perfect square, if the radicand is not a perfect square, the number is irrational. Students, I hope that you have got it. Now, third question, show that root 5 can be represented on the number line. See, I will try to make it a simple process, simple way for representing root 5 on the number line. And in this way, any any irrational number can be plotted on the number line. Here we are required plot root 5 on the number line. See how I proceed, how I explain these problems. What is the radicand? The radicand is 5. We have 5 is equal to, try to express the radicand as the sum of two perfect square number. Very easy. 5 can be written as 4 plus 1. 4 is a perfect square, 1 is also a perfect square. So 5 can be written as 2 square plus 1 square, or taking the positive square root, we get root 5 is equal to under root 2 square plus 1 square. Now, we are going to plot root 5 on the number line. We know that we will give this sign. We will write two perfect square, one smaller than 5 and the other one greater than 5. Smaller than 5, the perfect square number is 4, and more than 5, that is 9. Or root 4 smaller than root 5, smaller than root 9, 2 smaller than root 5, smaller than 3. Therefore, root 5 lies in between 2 and 3 on the number line. So this is one finding, and this one is the breakage of root 5. Now we are going to plot root 5 on the number line. Pay attention. We will draw a number line. Draw. This is the origin. This is 1. Equidistant 2, at equal distance 3, equal distance 4, and likewise 5, and likewise. So, two components, 2 and 1. We will take 2 units along this, 2 units. So, the point A on the number line represents 2 units. OA stands as 2 units. At the point 2 is covered. Now we have to take 1. At the point of A, we will make a 90-degree angle. A perpendicular we draw. We dropped a perpendicular. Second component is 1. We will take 1 unit. This is 1 unit. This is 1, 1, 1, 1. We will take measurement of 1 unit. It can be 1 centimeter, it can be whatever equal divisions are there. We will take 1 unit from this perpendicular line. This is B. What is the measurement of AB? AB measures 1 unit. So 2 units here, 1 unit, and this angle is 90 degrees. We join O with B with the help of a straight line. See, and triangle AOB, this is A. Triangle AOB is right angle at A. Therefore, by Pythagoras theorem, OB square is equal to AB square plus OA square. AB square 1 square. OA square 2 square, that is 1 plus 4. OB square is equal to 5. OB is equal to root 5. Therefore, by applying Pythagoras theorem, we have got that OB is equal to root 5, and this OX is the number line. Now what we have to do, we have to represent this root 5 on the number line. So we will take the compass, we will put the needle of the compass at O and tip of the pencil at B. This length is root 5. By putting the needle of the compass at O and tip of the pencil at B, we will draw an arc. Wherever this arc is intersecting the number line, let that point be P. The point P represents, that is OP represent root 5 on the number line. Why it is so? Because O is the center, OB is the radius, and OP is also the radius of the same circle. OB calculated as root 5 by Pythagoras theorem. Therefore, OP will also be root 5. Thus, the point P on the number line represents root 5 when O is treated as the origin and OA represents two units and AB represents 1 unit. I hope you have understood. So two important things you have to keep it in your mind, that first, where the given irrational number will lie, and for finding its position, what we have done, we know that 5, give these two signs and write a perfect square immediately before 5 and a perfect square immediately after 5. This is 4 and 9. We will take the square root. Square root of 4 is smaller than square root of 5. Square root of 9, that gives us 2, smaller than root 5, smaller than 3, which means root 5 lies in between 2 and 3. Second thing, we will try to break the radicand in such a way that it can be splitted as a sum of two perfect squares. 5 can be written as 4 plus 1. 4 is a perfect square, 1 is also a perfect square. 5 is equal to 2 square plus 1 square. Now, we have drawn the number line. We will take 2 units along this or on the number line. OA represents 2 units. At the point of A, we have drawn a perpendicular lines, and from that perpendicular line, we have taken AB as 1 unit, and we have joined OB. OAB is a right angle triangle, right angle at A. It is a right angle triangle with base 2 units and perpendicular 1 unit. By Pythagoras theorem, we are getting OB as root 5. Now, taking BO as center and OB as radius, we draw an arc which intersects the number line at the point of P. OP is equal to OB, and it represents root 5 on the number line. In this way, we can represent any irrational number on the number line along with the rational numbers. So friends, we have completed this exercise of 1.2. In the next class, we will see the decimal expansions of real numbers, and we will discuss the next exercise, that is 1.3, in the next class of ours. Till then, goodbye.